Hello and welcome to this edition of Coast and Country, powered by the science of the Connecticut Agricultural Experiment Station. Coming up in this special edition all about entomology, we talk with Dr. Haney Dweck about his groundbreaking work and research into chemosensory mechanisms and their role in insect-plant interactions and insects' abilities to adapt to new environments through sensory systems that evolve to allow insects to become agricultural pests. And Dr. Kelsey Fisher talks to us about her ongoing research into insect movement and dispersal ecology, as well as insect behavior, particularly related to the monarch butterfly, plus conservation of our pollinators like bumblebees, as well as agricultural pest management. But first, what exactly is entomology, and why is there an entire department devoted to it at the Connecticut Agricultural Experiment Station? I sat down with Dr. Gudaz Malai, Chief Scientist and Head of the department, to find out more.
Department of Entomology is a department that, in line with our institutional motto, that contributes to three major objectives and goals. One of them is protecting health and well-being of citizens of our state. The second one, protecting agriculture, and the third one is contributing to the environmental health. So as a result, we have three important disciplines in our department: agricultural entomology, public health entomology, and also environmental entomology. By public health entomology, we have two important discipline or line of work in the department. One of them is investigating the role of mosquitoes in transmission of arboviruses in our state and throughout the region. We also have tick and tick-borne disease research programs that investigate similarly the role of ticks in transmission of tick-borne diseases. With regards to research implication, of course, the research that we are doing in our department in the area of medical or public health entomology has broader significance for the nation and throughout the globe, and we are contributing in that regard. With regards to agricultural entomology, obviously we are helping farmers. We are helping those who are either having their own small garden or at a larger scale they have agricultural activity, and even for those who work in forests. So we have programs and plans and research activity for all these areas related to entomology in order to support growers, support our environment, and so on and so forth. Then in addition to that, we have two important service sections in our department. One of them is the Insect Information Office, where we receive inquiries from all over the state. No matter what the topic is, they bring their insects to us or they bring their questions to us. These could be agriculturally important pests, or they could be structurally important pests or environmentally important pests. They bring to us and we provide them with information. Another important service program that we have here is the tick testing laboratory. Tick testing laboratory has been in place in our department for the past 4 decades, where we receive ticks, up to 6,000 ticks from residents, and these ticks are inspected, evaluated, and tested, and the results are communicated with public in order to inform them and help them to make a decision concerning diagnosis and treatment of tick-borne diseases. Another line of work that we have in our department is the regulatory entomology, meaning that we have a subdiscipline, a team of people who are mandated to regulate imports and exports of all agricultural items to the states and from the states to make sure that they are free from pests and disease agents. In addition, we also have a statutory responsibility to inspect apiaries, and we have a research technician who does this work to make sure to support those who are in the business of bees, and also making sure that all the aspects, environmental aspects of beekeeping is addressed. Considering what the outlook or the future of entomology will look like as a result of climate change, we are going to be dealing with a lot of invasive ticks and mosquitoes, as well as agricultural important, as we are already dealing. And as the climate change situation gets more severe, then we have planned, we are working on various disciplines in order to be prepared to deal with events that we will witness as a result of climate change.
So I work with bumblebees and monarch butterflies, and the big focus of all of the research that I do is understanding landscape scale habitat connectivity. So a lot of times people think about seeing a monarch butterfly in their backyard or bumblebees in their backyard foraging in their garden or on their flowers. Something to remember is that those insects don't live in your backyard. They're just visiting for a short period of time. And they also visit other people's backyards. So your backyard potentially could be a habitat for these insect pollinators. But things like roadways and parking lots and other forests maybe could serve as what we as population ecologists call the matrix. So it's places that are not good. So we have habitat and matrix. And so it's a lot of the work I do is trying to understand how our pollinating insects are navigating the matrix to find where the good habitats are. And if you have lots of things that are considered bad habitat or matrix, then it makes it more difficult for those insects to navigate from one garden to another garden. So if we understand how they're going from one spot to another, we could potentially establish additional habitats to make that movement more efficient. So rather than having one garden on one side of the town and another garden on the other side of town, maybe we could figure out a way that the insects could determine where the next place is if we establish stepping stones of habitat, so they could efficiently move from one spot to another. With the monarch butterflies, one of the things we were trying to figure out is that where do they go next? When they're in your backyard, they're there for a little while, but where are they going next and how are they getting there? And one of the things that we really noticed because of the radio telemetry we were using was that these butterflies can take flight steps of over 2 kilometers. So they can take these really large steps. But we were really interested in when their movement or when the direction that they're moving is modified by a stimulus. So if they can detect that there's a flower and they go directly to the flower, and what distance that could be. Because if we could establish habitat patches within their perceptual ability, then they would be able to efficiently move from one spot to another spot. And so I was doing some field testing to understand how far monarchs can see and smell. And we were noticing that even though they can do these flight steps of over 2 kilometers, most of the time their behavior was modified within 50 meters of where they were located. So the recommendation from all the work that I was doing with monarchs is if we could establish pollinator habitat every 50 meters, we'd be able to create a functionally connected landscape. They'd be stepping stones for those monarchs to go from one to another, and it would be really efficient for them. Find milkweed and find nectar and all the happy things. That's not necessarily a realistic recommendation. So thinking about that in mind, if you're going to be putting in a pollinator garden, to be thinking about where are other pollinator gardens in your town to create a better connectivity. And I always say that it's great if you put milkweed in your backyard, but it's even better if your neighbor does too. So then they can hop from one backyard to the other. I'm also going to be putting the transmitters on bumblebees. And hopefully with that, rather than looking at how they're moving, we're going to use that technology to understand where they're nesting and where they're overwintering. So the bumblebee queens make habitat selection decisions for their colonies. And it seems silly because we feel like we know a lot about bumblebees, but their nests and their overwintering locations are incredibly cryptic, and we don't really have a great understanding of where they are. So in order to provide conservation or habitat restoration that would support nesting sites and overwintering sites, we have to know what they are. So we're going to be using the telemetry to try and find some queens when they are looking for those habitat areas. I'm also going to be working a little bit with spotted lanternfly to understand its natural dispersal. So spotted lanternfly, we know, is a hitchhiking insect. So I feel it's in the news all the time about how they're on your cars and you need to check to make sure you're not taking them with you, or they lay eggs on your patio furniture and things like that. And that's a big way that the insect is moving across the country and across state lines and things. But once the insect is somewhere, we don't know how it's going to invade the landscape. So spotted lanternfly is often in roadsides, highway roadsides, and also at rest stop areas, because they'll hop off of the cars at those places. But we don't know how long it's going to take for them to go from those rest areas to our vineyards, which is where we're really concerned about spotted lanternfly. Spotted lanternfly is an economic pest of grapes. So our grape producers are the ones that we need to be concerned for. The things with climate change and monarchs is it's definitely expanding their host range for milkweed. So the monarchs follow the milkweed, and the milkweed is going further north into Canada. And with the monarchs, they overwinter in Mexico. So if they are caterpillars in Canada and they become an adult butterfly and need to migrate all the way south to Mexico, it takes a lot more energy for them to move from further north to further south. We don't necessarily know how much of an impact that's playing on the population decline, but it might be part of it. The warmer springs and warmer falls are definitely something that I'm noticing every year.
So I'm a chemical ecologist, and my laboratory studies the chemical interactions between insects and their environment. Insects use chemical signals to find the host plants, to identify suitable feeding sites, to mate, to aggregate, and to select suitable spot to lay eggs, as well as to avoid natural enemies. In turn, insects has evolved very sensitive sensory organs to detect these chemical signals and convert them and convert the chemical language of the external world to the electrical language of the nervous system. So my research is dedicated to identify these chemical signals and dissect the mechanism behind their detection, as well as determine their ecological significance. This work holds the potential to identify novel natural attractants and repellents, and also holds the potential to develop innovative solutions to manage agricultural pests as well as health problems. The main focus of my laboratory is on spotted-winged Drosophila. So spotted-winged Drosophila, native to Southeast Asia, invaded California in 2008 and was found in Connecticut in 2011. It quickly moved across the United States and has now emerged in Europe as well. This species is a serious pest to a wide variety of fruit crops, including strawberries, raspberries, blueberries, grapes, and many other fruits. To lay eggs on fresh ripe fruit, this species has acquired a large egg-laying machine to lay eggs or to cut through the skin of fresh ripe fruits and lay multiply eggs, while other Drosophilidae species, they have a machine that cannot cut through the skin of fresh ripe fruit. This species also has evolved an egg-laying preference for ripe fruits, while closely related Drosophilidae species lay eggs on fermented fruits. So my laboratory is interested to study the mechanisms by which this species select ripe fruit for egg laying, as well as we are interested to study how did this radical difference between the species evolved and allows this species to lay eggs on fresh ripe fruit. So one of the projects that we're running in the lab is aiming to identify novel natural repellents in agriculture settings and dissect the mechanism by which these repellents are detected. And the foundation is simply came from the fact that the spotted-winged Drosophila don't like fermented fruit to lay eggs. So this suggests to us that fermented fruit could contain compounds that discourage spotted-winged Drosophila from laying eggs. So first what we did, we collected odors, volatiles, from about 28 different fruits at the fermented stage. Then we analyzed the chemical profile of these fruits using gas chromatography mass spectroscopy. This turned out that these fruits contains about 11,000 chemical compounds. This is too much. So what we did a comparison of the structure of these 11,000 compounds to known insect repellents, such as DEET, the worldwide used insect repellent. And then we found just a small group of 19 fruit volatiles are very similar either in their shape or structure to the known repellent. And then we tested this, and we started to hypothesize maybe one of these compounds will discourage spotted-winged Drosophila from laying eggs on ripe fruits. So we tested this in the laboratory. 15 out of these 19 compounds elicited a strong egg-laying avoidance in Drosophila suzuki. And indeed, some of these compounds provide 100% protection for the fruit. Now we are transitioning from the lab experiments to the field, and we're starting with a greenhouse, then semi-field at Lockwood Farm, and then a field. And hopefully at the end we will sell this product, and hopefully we will help protecting our valuable fruits from this pest. Our work aligns well for the case mission, which is putting science to help community. So first we address agriculture problems or public health problem, and not only addressing them, not only studying them, we also provide solution. Like now we try to develop lures and repellent to protect our crops, but we also train undergraduate students around us. So from the colleges around us or universities, we also recruit postdocs and train them. This is our next generation scientists. Plus, we also deliver our research in publications. This is the most recent set of publications that we able to produce in the lab. And some of this publication, it deals with spotted lanternfly. It's another invasive species that the state try hard to protect our resident and agriculture as well from them. And here we identified several new chemicals that can be used either as attractant or as repellent, and hopefully this can turn to something we can use it in the field or in the forest. You know, this species is just going everywhere, anywhere. So this is one of the this is show how our work align well with the case mission. We focus on chemical ecology and the interaction between insects and their environment. So our aim is to develop environmentally safe strategies to protect the community. So they have to know that we actually not only develop things, we are upfront. Whenever emerges to the state, we go and try to understand from them. We have our doors down open to the public to learn from them about the problems they face daily, every day. As you can see, the office down has many visitors every day, and we just not only report whatever they told us, we go to there and investigate the problems, and we are upfront, but also we also care for their health. So we try to develop innovative ways that depend on natural product to protect our crops from the harmful insects.
That's all from this edition of Coast and Country. If you want to find out more about the work of the Department of Entomology at the Connecticut Agricultural Experiment Station, then visit their website at ct.gov/CAES. Details are on your screen now, and search for Entomology. I'm Brian Scott Smith. Thanks for watching. We'll see you again soon.